Hello students, so in this lecture we will be discussing in details what is the Gibbs phase rule. Now mathematically, as you can see, the Gibbs phase rule can be expressed as F is equal to F is equal to C minus P by 2, where F is the degrees of freedom and C is the number of components and P is again is the number of phases which are in equilibrium. So this is the Gibbs phase rule. Now we will take up each of the different parameters and try to understand it in a more in depth. When we talk about phase, like this one, phase P, in the case of an iron carbon diagram, uh, there is a phase called ferrite, there is a phase called pearlite, martensite, benite, austenite, and so on and so forth. And each of them has a different crystallographic orientation, like this ferrite has a BCC crystal structure, horizontal cubic. Then when you go to martensite, when you go to austenite, it has an FCC structure. Martensite has a BCT structure, and similar to pearlite has a different. It is actually a combination of ferrite and cementite in 1:8 ratio, and so on and so forth. So these are the different phases. By phases, we mean that they have to be physically distinct and chemically homogeneous. So there are two aspects to a phase. First of all, they should be physically distinct. Is the first condition, and the second condition is they should be chemically homogeneous. And when these two conditions are existent, they are mechanically separable region of a system. So the third aspect is sorry. It should be mechanically separable. Now, coming to components of system, that the C part, let us write down the expression once again. It's F is equal to C minus P plus 2, or sometimes it can also be written as F plus P is equal to C plus 2. So we have talked about the phase. Now we will talk about the number of the C, the components. So these components are basically, they can be elements, they can be ions or compounds. In the case of stainless steel, number of components is 2, because we are having an iron which is being alloyed with carbon. It can be homogeneous, it can be a single system component as well. It can be, for example, H2O. Number of components is again 2. Now here we will not considering however in this case in the case of an H2O we will not considering the elements, we will be considering the total state of the system. Okay, so the component is H2O. In the case of a copper nickel system, which is an alloy, uh, the elements are the components. So here number of components is 2. Okay, so in which case you are taking what is the characteristics or of the material, if that depends upon the percentage of or the fraction of the elements, then we are calling it as the components. Whereas in the case of an H2O, it doesn't matter. It is fixed. There is no variation of H2O in chemically. So the number of components here is not 2, it's 1. Okay. So this was all about the components. Now degrees of freedom is again usually we can degrees of freedom means in what ways or we can have the different phases. Okay, like in the case of iron carbon diagram, we can have 2 degrees of freedom, that is a temperature or carbon concentration, weight percentage. These are the 2 degrees of freedom. Likewise, you may have temperature, pressure, different parameters which defines a phase other than degrees of freedom. Now the composition, the C part, are normally expressed as weight percentage. If you look into the iron carbon diagram, so you have a temperature on the y-axis, the ordinate, and you have carbon weight percentage on the x-axis, and you get different phases in the case of iron carbon diagram. Now, so if with the composition expressed as weight percentage or atom percentage, now the number of variables required to specify completely a composition of a phase is C minus 1. Okay. And, so where C is the number of components of the system. If this is the number of components and this is what the weight percentage thing does to the expression. Now, knowing the percentage of C minus 1 component, percentage of this, it automatically fixes the percentage of the last component. So if this is known, it will automatically fix the percentage of the last component. Now again, if P is the total number of phases, so the total number of composition variables, so this is number of the phases at equilibrium. Again, if you multiply P with C minus 1, then it gives you the total number of composition variables. So if we include the two external parameters like pressure and temperature, so these are the external parameters taken as temperature and pressure. The total number of variables then is P into C minus 1 plus 2. Now, out of these number of variables, the number of out of these the number of independent variables it will give you the degrees of freedom, that is your F. Now this F cannot be more than the total number of variables, since F has to be less than, at least less than equal to C minus 1 plus 2. So if that is the case, then you can write it as P F, which is equal to C minus P plus 2 as per Gibbs rule or Gibbs relation, and it is less than P into C minus 1 plus 2. So from this system we can just observe that only one phase is present in the system. Okay. So it shows that only one phase is present, since for this equation to be valid, P has to be equal to 1. So we can conclude that degrees of freedom are in this case, of course, the degrees of freedom DOF, or F for that matter, is equal to the total the degrees of freedom is total number of phases, or the total variables. Now, as the number of phases increases, the total degrees of freedom will decrease. So since this equation has to be maintained, so an increase in P will cause a decrease in F. Right. When degrees of freedom cannot be less than 0, F is not cannot be less than 0. So we have an upper limit to the number of phases that exist in equilibrium. So this gives us the fact that there is an upper limit to the number of phases that can exist in equilibrium.